Hello students, welcome to another lecture. Today we are going to discuss size reduction. Okay, so this is chapter 29 uh, of that unit operation book. So what do you mean by size reduction? So you want to reduce the size of the solid particles, right? You already know, right? We have there are crushers to crush big rocks into small rocks, right? So you're reducing the size so that it can be useful during construction work, right? So that's why, because size reduction is very important because of the products you need. So this huge rock may not be useful, but if you crush it into smaller particles, then it will be useful, right? So that's why there are different applications in industry. Like you have a big chunk of sugar crystal. Now this you cannot sell to the people, right? So you have to crush it to, like some coarse particles. Now you can sell it, right? Also, if you use a big chunk of sugar and you just put in the hot water, then it will not dissolve because it has very less surface area, right? But if you make it into smaller particles, then this sugar crystals have very small surface area, so it will be easily dissolved. So there are different motivation, right? So so size reduction is very important in industry. Okay, so now, so in this chapter we will be studying the size reduction process. What are the laws, principles, what are the equipments to achieve those size reduction? Okay, so we have four ways how you can break solid. Okay, so there are four processes in which you can break a solid into smaller particles, right? There are mainly four processes. So the first one is compression. Okay, so yeah, where basically solids can be broken in different ways, but only four of them are very commonly used in size reduction machines. Compression means you're like compressing a solid, right? By applying force on the both sides, then it will get crushed. Okay, that is called compression. For example, nutcracker. You have seen nutcracker. If you want to crack walnut, then there's this tool called nutcracker, right? You can use that. So this is a basically example of compression. Fine. Now next, impact. You can break the solid using impact. Also, what do you mean by impact? Suppose you hammer it. If you have a hammer and if you hammer a solid, then it will break into pieces, right? Smaller pieces. So that is called impact. Okay, so the best example will be your hammer. For compression, nutcracker. Next, third one is your rubbing or attrition, right? So rubbing or attrition, this is the third way how to reduce the solid size. So the best example will be a sandpaper or filing. File. You can file iron pieces. Using sandpaper, you can also file metal plates or wood, right? So if you rub with sandpaper, then also it becomes smooth, or you can reduce the size, right? This was the third way. The last one is the cutting. You can directly cut the solid if you have a proper tool, right? to give it a desired shape, so you can reduce its size. For example, you use to cut the glass, you use diamond, right? Diamond cutter. So using diamond cutter, you can give any shape to the sheet of glass, right? So that one is the fourth one, right? Cutting a pair of shears, or you cut you cut with the help of scissors, right? You cut paper with the help of scissors. That is also an example of cutting, right? These are the mainly the four ways in which you can reduce the size of the solid. Okay, so but these four processes will give different size of the products, right? So if you do compression, or you compress it, then it will give coarse particles, right? Hard solid. So it will not give you very small particles. However, if you use impact like hammer, you will get fine particles, right? Smaller, very fine. And if you use attrition, then you will get very fine particles, right? Very fine smooth particles. And thirdly, if you use cutting, then you will get a definite shape. You will not have any fines, but you can give a desired shape to a solid using cutting. Okay. Okay, next. Next, we say here principles of comminution. Okay, what do you mean by comminution? This is kind of, scientific term for size reduction. So size reduction means comminution as well. Comminution. So the meaning of comminution is also size reduction. Okay. Now, like, let's say you have a equipment or a machine which is for comminution or size reduction, right? So what are the ideal properties? I mean, ideal, right? Ideal properties I expect from that machine, right? So the ideal properties are something like this. They should have a large capacity. Large capacity means if you have that ideal size reduction machine, large capacity is you can put as many feet as you like, right? You can go on putting huge amounts of feed, so it can handle those huge amounts of feed, right? Then it is an, ideal size reduction equipment. Next, to be ideal size reduction equipment, it should have require very small power input per unit of product. Suppose I want to produce 1 kg of product, like fine particles, right? So if it is requiring 1,000 kilowatt, then this is useless, right? But if it is doing the same job in 1 watt, you are putting in very small power to get 1 kg of product, then this is also a very good size reduction equipment. So it should require very small power input, right, per unit of product form. Okay. Third one, yield a product of the single size or the size distribution desired, right? So third one is like, if the machine does not give you the size you desire, then it is useless, right? So suppose this is machine, you are putting feed here and you are getting product. You need, let's say, fine particles of diameter like 1 millimeter, right? But this machine is not giving you 1 millimeter, it is giving you 5 millimeter. Then this machine is useless for me, right? Okay. Also, this machine should give you, suppose this machines give you 1 millimeter. This is the, you want this, the product to be of 1 millimeter size in diameter, right? But suppose this machine does not give you uniform distribution in the sense it gives randomly. So one particle of 1 millimeter, but other particles of different sizes, right? This is also I don't want. I want uniform distribution. Like if this is 1 meter, so each and every particle is of 1 millimeter in diameter. So this is the uniform size distribution, right? This ideal size reduction equipment should give you uniform distribution. So this is like ideal crusher grinder should be like, right? This is ideal. This does not exist in reality, right? But if the machine is as close to this qualities, then it is almost ideal candidate, right? But in reality, this is not a possibility. Okay, these properties does not exist. You take any industrial crusher or grinder, this they will not have, you know these properties, because these are ideal properties. They don't exist. But it is possible that this saturation equipments are close to these properties. They have close to these qualities. Okay, that is completely possible. So if you want to compare two machines, right, two crushers, right? Let's say A crusher, B crusher, right? So whichever whichever crusher have the qualities closest to these three, that you will choose, right? That will be the best crusher for a particular operation. Okay, so these are the criteria. Okay, so next, so what are the properties of the comminuted products? Okay, properties of the comminuted products means once you do the size reduction, then the feed is converted into product, right? So what should be the, or what are the characteristics of the products, right? So some general properties are given here. Okay, so definitely the first one is like, you in ideal crusher, what you expect, the product should have very uniform distribution, right? Every particle has same diameter, right? But in reality, this is, right, this is not possible. So we are talking about characteristics of comminuted products, right? Or size reduced products. Okay, so this is not possible for in the real. Okay, but it is possible if you use feed of uniform particle size distribution, then definitely you also get a uniform product in particle distribution, right? That is possible. So that was the first point, the characteristic of comminuted product. The second point is like, suppose I have reduced the size of particle from size 1 to size 2. What is the ratio, right? Let's say I have reduced this size into this product, right? Let's say definitely this will not give you uniform particle size distribution, right? But it will give you something like non-uniform particle size, randomly particle sizes. So if you take the ratio of this smallest, no, largest particle in this product. So what is the largest particle? Let's say you have diameter of the largest particle, dp largest, and dp and the smallest one. If you take the ratio, then you will get a order of 10 to the power 4. That means, suppose I crush some feed and I get the product, right? So suppose this means that the smallest particle would be if the smallest particle is 1 mm, then the largest particle will be 10,000 mm. Okay, so this ratio 10 to the power 4 ratio will be almost maintained in every crusher. Okay, so this is point 2. Okay, the third one is like the third characteristic of the comminuted product is that the products after size reduction process, the particles will not be smooth. Okay, it will be some polyhedrons or random. It will not be smooth. It will not be smooth as like spherical particle. It will have very sharp corners. It will have a lot of faces. Okay, so you can, if you want to have smooth products, then you have to use that attrition process to get the smooth smooth products. Okay, okay, this were the characteristics of comminuted products. I mean the solid particles which has undergone the side reaction. Okay, so next we'll have we'll see crushing loss. Okay, so so what are crushing laws? So we have to study crushing laws. Why crushing laws are needed? Because suppose you have a feed of diameter dpa. Okay, this is in feed. The feed has the average particle size of dpa, and you want to reduce this size to something dpb. So this is the average particle size of the product, right? So you want to do size reduction, right? You put in some crusher. Okay, now tell me how much energy you need to reduce the particle size from dpa to dpb, right? So to predict the energy required in terms of power, I mean watt per ton of the feed. Okay, so in crushing operation we don't deal with kgs, we deal with tons, right? 1000 kgs. Okay, so my question is like how much energy you need to crush this feed from 1 ton of feed from DPA to DPV. So using crush laws we can predict the energy required. Okay, so let's derive the formulas. So and a power required, a power input required for various crushers. Okay, first we'll have crushing efficiency. What is the crushing efficiency? So crushing efficiency is like how much uh, energy is absorbed by the solid particles. Okay, it's kind of ratio. So we denote the crushing efficiency by eta c. C stands for crushing. So it is basically ratio. What is the ratio? I'll explain. Wn. First write the formula. A WB minus AWA. Okay, A B means the A means feed, okay, B means the product. Fine. So crushing efficiency basically it is a ratio of a new area or surface energy created divided by the energy absorbed by the solids. So suppose you have provided energy to the solid for crushing. Obviously if you compress this, it needs energy, right? So let's say you have supplied some energy, but the energy absorbed by the solid is Wn. Let's say Wn is the energy absorbed by the solid. Okay, then definitely it will get crushed, right? Let's say it has crushed into like this, these particles. Okay, surface energy is like nothing but energy per unit surface area. Okay, so definitely the new surface area will be what, this surface area of this minus this, right? Or the energy surface area of the product minus surface area of the feed, right? Because the surface area of the product will be higher than the surface area of the feed, right? So definitely this one, right? The AWB minus AWA is nothing but the difference between the surface area of the product minus feed. Okay, and you now know how much new surface area is created, right? So this difference will tell you the new surface area created, and you know the surface energy of a particular solid. So surface energy is nothing but, let's say, joule per meter square, and you're multiplying with surface area, so that is meter square, so you will get energy, right? So this much energy is created while crushing it. Okay, and how much energy absorbed by the solid? Wn. What does it mean is W n will be used to crush the solid, right? But in reality what happens is, uh, this total energy will not be, this energy will not be entirely converted into used to crush the you know uh, these solid particles. Some will be wasted in the form of heat, sound, okay, friction, energy. So there will be very much more energy loss than the actual energy absorbed, right? So this is the energy absorbed by the solid. Some of this energy will be used to create new surface area, okay, but rest of the energy will be gone as heat, sound, and frictional heat. Okay, so that is how we define crushing efficiency. Okay, so you can read here what is given. Okay, so you can read here, so same thing. Now this is efficiency, it doesn't have any units. Okay, what is Wm? This energy absorbed by the solid particle. Okay, so it is joule. So joule, right? So Es is what? Joule per meter square. Okay, and what is this AWB? We already discussed in previous classes. AW is nothing but specific surface area, right? So it should be in the unit of meter square per kg, right? Specific surface area. So here you'll get joule per meter square. Here joule per meter square, and here you have meter square per kg. So you will get joule per kg. Now this is dimensional, right? So if it is dimensionless, then the Wn, the energy absorbed, should be also in joule per kg. So it will be provided. So how much energy is absorbed per kg of the solid? Okay. So this is your crushing efficiency. Okay. Now we'll define mechanical efficiency. What do you mean by mechanical efficiency? Okay. So we'll now define mechanical efficiency. So this is defined by eta m. Again, it is dimensionless. So it is defined as like this: Wn by W. So so mechanical efficiency basically relates with the machine. Okay, that size reduction machine. Fine. So W is basically energy input to the machine, right? You are putting some energy like through electrical inlet. Okay, you are putting through power. Okay, so let's say this is the energy you have put in this machine. Basically, it will be in the form of electrical energy, right? So current. So you put it and you'll get the products, right? So what happened if you put W energy into the machine? Then, but what is Wn? I already told you, it is the energy absorbed by the solid. Okay, so you are putting W energy, but some of the W will be only absorbed by the solid. The rest will be lost as what? See, these size reduction equipments have, it has gears, very heavy parts moving, right? So because of the frictions of this gear and these moving parts, then there will be a huge loss of energy. Okay, so even if you put huge energy to the machine, all of the energy will not be absorbed by the solid. Only some fraction will be absorbed by the solids. Okay, so this is the definition of mechanical efficiency, right? Okay, now you can calculate the mechanical efficiency in terms of the other calculated the other values which can be calculated, right? So so I'll write down, so from previous one. So so mechanical efficiency is nothing but Wn by W, right? Now I will rearrange because I told you to find the crushing loss. You are basically calculating the how much energy is required to reduce a feed of size, some certain size, to product of certain size, right? So I am much interested in the energy input. So I will rearrange W is equal to Wn by eta m. Eta m is the mechanical efficiency. What is Wn? This is related with the crushing efficiency. So if you rearrange this equation, so eta c will be Wn will be this. So es awb minus awa, okay, and eta c, and this eta m. So this is how you define. Okay, now if you do the dimensional analysis, the unit of this should be somewhat kg per hour, or it will be in ton per hour, because we are deal with very large amount of solid, so it should be in ton per hour or kg per hour. Okay, so what will be the power? What is power? Now you can calculate power, right? What is the power? Power is defined as rate of doing work, right? W by time. So you know energy per unit hour, right? No, no, sorry. This is the if you calculate the W unit should be in joule per kg or ton. Okay, because this is your surface energy, that is joule per meter square. Okay, surface energy will be joule per meter square. And what is the specific surface area? Meter square per kg, right? So joule per kg. So the work, the energy input is in the terms of joule per kg. Okay, so W is in the terms of joule per kg. So but but so it is joule per kg and unit per unit time. then only it will be power, right? So if you multiply with, so if you rearrange this joule per kg into time, so if you can somehow remove this kg, right, then you'll get the power, right? So to remove this thing, instead of using divide by this time, what I will do is I will multiply with mass flow rate. Okay, m dot. So what is m dot? It is nothing but kg per hours. Now it cancels out joule per hour. Joule per hour will be nothing but in the power, right? So that's why in this, if you see this formula, it is multiplied with work input into m dot. So this is mass flow rate of the feed. Okay, it will be generally in the tons per hour. Okay, so this will give you power. So the formula remains same. So now you have got the power formula. How much power is required to reduce the feed size of A to the product size of B. Okay. So sorry, power is equal to m dot es awb minus awa by eta c eta m. Okay. Now I will simplify this equation further. So what is this specific surface area formula? So specific surface area formula is AW by 6 sphericity phi s rho p and the volume surface mean diameter, right? ds. Okay. So you can put it here. Only the difference will be if you are calculating for the feed A, then it will be A. If you are calculating for the product, then it will be this B. And also here it will be changed A or B depending on. So if you put here, so how what you will get now? So power will be equal to m dot es. Now you can put here. So that will be eta c eta m 6 by sphericity phi b, right, rho p dsb volume surface mean diameter, then sphericity of the feed A rho p dsa volume surface mean diameter of the feed. Now sphericity will be generally constant for a solid, so you can assume that sphericity is same for feed in the product, so you can take it out. Again, density, you can assume that density are same of the feed and product, so you can take it out. Again, you can take it out the 6 value, so you will get what you will get. Finally, get power is equal to 6 m dot es eta c eta m rho p pi s 1 by dsb minus 1 by dsa. This is volume surface mean. So this is what you got the formula, right? So this is the final formula. You can also see in the textbook the same formula has been derived. See, you came to this one. So this sphericity is assumed to be constant, so it is taken out. Okay. Now I can make this very simple. So now that's why the laws, commutation laws came in. So first we will discuss Rittinger's law. Rittinger's law. So Rittinger's law, this law is based on what? This crushing is the work required in crushing is proportional to the new surface created, as defined previously, right? We have derived based on the surface energy created only. So this is nothing but Rittinger's law. So what you can simply write this formula as P by m dot. So m dot is in ton per hour, P is the power input, and just replace the constants with Kr, 6 Es eta C eta m phi s sphericity into rho p. So that will be equal to Kr, and you are left with 1 by d SB. This is volume surface mean diameter, remember, SA, right? So feed average volume surface mean diameter of the feed and the product. Okay, so this is your formula. This is called Rittinger's law. Rittinger's law. Okay. Again, the scientist he proposed another law. Right? So his theory was based on that the work required for crushing is given in a given mass of material is constant for the same reduction ratio. Kick's law says that the work required to crush a given mass of material is constant, okay, if the size reduction ratio is constant. Suppose we have a material a material, you want to crush it from size A to B. Okay, so this is feed size, and this, then the size reduction ratio will be A by B, right? So this reduction ratio will be constant for a given material. So this is the Kick's law. So it is given by P by m dot mass flow rate is equal to Kk. This is constant K, but this is constant K is given by Kick's law, so it is K. In the Rittinger's law, it was R, but here Kick's law it is K. So ln dSA. Remember, this is feed, huh? This is dSB. This is product. So this is the Kick's law. Okay. Now you can generalize these two formulas like this. So d P by m dot is equal to minus K d s, this is n, d power ns. Now if you put n is equal to 1, then you will get the Kick's law, right? So if you put n is equal to 1, this will 1. So if you integrate on the both sides, this will get P by m dot, and here it is 1 by x dx, right, in the form of this. So it will get ln ds by this. Okay, so if you put n is equal to 1, you will get Kick's law. If you put n is equal to 2, then integrate, then you will get Rittinger's law. Okay, so we have studied two laws, Rittinger's law and Kick's law, and we have one more law that is called Bond's crushing law. We can say Bond's law. Okay, or we can talk about work index. So according to Bond's law, he said that the work required to form particles of size dp from a very large feed is proportional to the square root of the volume to surface to volume ratio. He is saying that if you want to reduce the particles from very large feed, let's say it is infinite, the feed size diameter is infinity, and you want to reduce that from to size dp, then the work required will be directly proportional to the square root of sp by vp, surface to volume ratio. This is what Bond's law states. Okay, so if we follow Bond's law, then you'll get a formula So the formula given by Bond's law is this: P by m dot is equal to, here it is a constant and Bond's constant, so Kb square root of dp. Okay. You can ask here, there is no dpa or dpb. Okay, because the feed is basically, this is dpb, because in this case it is assumed that feed is of infinite size, so 1 by infinity will be 0. That's why here there is no dpa business. Okay, so this is the diameter of the product. Okay, now I just told you, right, the general equation for deriving all the laws. So if you see here, so this was the law, right? This is a generalization of these two laws. So if you put n is equal to 1.5, then you will get Bond's law. Okay, so in this formula, if you put n is equal to 1, you will get Kick's law. If n is equal to 2, then you will get Rittinger's law. If you put 1.5, then you will get the Bond's law. Okay, so sometimes this is very useful in GATE exam. They ask what is the value of n to get Bond's law, like, so they can ask any question. Okay, so you have got the Bond's law. Now there is called work index. So work index is related to Kb only, the constant, Bond's law's constant. So what is the definition of work index? So work index is defined as this. So work index Wi is defined as the gross energy requirement in kilowatts per hour ton. So what is the energy required? Kilowatts hours, watt hour, right? This is watt hour, that means the energy only, per ton, of the feed. Okay, needed to reduce a very large feed to such a size. So what is the work index? It is basically the energy requirement. What is the unit of energy that required? That is kilowatt hour. What is the feed weight? 1 ton. Okay, so energy required to reduce the size of 1 ton feed. Okay, okay, so from very large feed, the feed size is infinity, to a size such that 80% of the product passes through a 100 micrometer screen. Okay, then that is the work index. So if this is true, then the relation between the Kb and Wi is, so Kb will be given as something like this: 100 into 10 to the power minus 3 Wi. So if you calculate it, it is 0.3162 Wi. This is how Kb is related. Okay. Now you can get a different formula for Bond's law. So it's like, if 80% of the feed, so you have a feed whose size is such that 80% of this feed will pass to the PA millimeter screen, and you have a product from which 80% of the 80% is like mass fraction, 0.8 mass fraction of that product will pass through of dpb millimeters. Okay, you have to remember these units, otherwise it will be wrong. You cannot use the formula directly without converting to appropriate units. Okay, So if this is true, then the new definition of the Bond's law will be power by m dot is equal to 0.3162 and 1 by square root of dpb minus 1 by square root of dpa. Remember, here it is not volume surface mean diameter, it is simply the screen size. Okay, don't get confused. So this is screen size, not the volume surface mean diameter. So you can easily calculate if you know that 80% of the feed passes through the screen opening of dpa and 80% of the product passes through the screen of opening dpb. Okay, so this is the formula, you just remember it. Okay, let's solve one problem, then it will be clear. So there, this is the table. It is the work in this is given. Okay, wi is given for some certain type of material like bauxite, aluminum ore, cement, raw material, clay, coal, coke, and limestone, CaCO3. Okay, specific gravity means what? What do you understand? Specific gravity is like density of that material. Let's say I want to calculate the SG. It is called SG, specific gravity. So if I want to calculate the specific gravity of certain material, let's say limestone. So density of limestone divided by density of water. Okay, that is the definition of specific gravity. And it is given work index, right? So work index for limestone is 12.74. So let's solve a problem. Okay, what is given here? So what is the power required to crush 100 tons per hour? See, mass flow rate is given, m dot is given, and 100 tons per hour of limestone. The material is given, limestone. If 80% of the feed, okay, passes a 2-inch screen, so it is saying that screen size is for feed is 2-inch, okay, and 80% of the product passes through 1 by 8-inch screen. So feed dpb is equal to 1 by 8 inch, right? So take the Bond's law. According to Bond's law, we have what is the power requirement? P by m dot is equal to 0.3162 wy, right, into 1 by square root of dp b minus 1 by square root of dpa. Okay, but remember, the work index doesn't have any units, it is dimensionless, right? But you have to use dp in millimeters only. Don't use other units, don't use meters. No meter, no centimeter. Okay, only millimeter or no inch. You cannot use these units in this formula. Okay, so only you have to use the millimeter formula. But in the problem it is given as 2-inch. So if you want to convert it into millimeter, what is 1 inch is equal to 2.54 centimeter, right? 2 into 2.54 centimeter, and 1 centimeter is equal to 10 millimeter, right? So 10 millimeter. So you can easily get. Similarly here 1 by 8, first convert inch into centimeter, 2.4 and centimeter into millimeter, just multiply it 10. So you'll get this. So they have calculated here, again here. So you have found, just put it here. So you don't know work index. So from the previous table, I have shown you that the work index is 12.74, right? So you just put it here, and this mass flow it is given, just multiply here, right? So you can see here all the values put here. You can calculate easily. Okay, the unit, you do appropriate units. It can be kilowatt. The unit should be in kilowatt. If you get kilowatt hour, that means it is the energy. Okay, kilowatt hour is the unit of energy, not power. Only watt is the unit of power. Okay, in the next class we will discuss some of the equipments like crushers, grinders, what are the different types of crushers like jaw crusher, smooth roll crusher, ball mill, and so on. Right? We'll just go through those. Yeah, thank you.